This is like my A-level chemistry knowledge. I've forgotten already. Wait, moles is no more Mr. Nice Guy.
Are you dense? Crank up the volume and go with the flow. The Full Story is an episode of the Degrees of Freedom project. The Full Story videos on chemical and thermal principles, definitions, and additional details can be found in the webpage link in the description. What is the relationship between density and specific volume?
Because like density is a relationship between mass and volume, right? So if you want to calculate a volume of something, if you know the specific density of it, and if you know the mass, you can calculate the volume, or vice versa. If you know the volume, you can kind of calculate the mass in some way.
Density is mass over volume. Is that it?
Well, I would probably say mass, because density is like mass over volume, right? And the specific volume is volume in specific volume. Is it volume? No, it's not volume over mass. Volume over
maybe.
Is it volume over mass? Is it like the reciprocal of each other?
Okay. Well, density is your mass per volume. Specific volume. Don't remember.
They're just inverses of each other. So, your density is mass per unit volume, and your specific volume is volume per unit mass.
How do you use specific volume?
Specific volume? I'm not really sure about that.
I don't know what the difference is between specific volume and volume. The specific volume, I guess, just refers to the volume of the container. I don't know. I've never come across a term specific volume before.
Got it.
I don't know how specific volume is used. I think if I did, I could maybe get the units from that. Figure something out about that.
Oh, and like flow rate calculations. It's like Q dot is equal to like the specific volume times, I think, like density times area. No, it's volume times. I can't say this one right now.
It's used a lot in kind of thermal problems. Usually I end up using it if I'm in the vapor dome or something, just as one of my variables to define my position, so I can do table lookups and stuff.
This video discusses some of the basic process variables that are used in most chemical processes and found in many other engineering processes as well. The mass density is usually given the symbol ρ and is usually just called the density. The mass density is a measure of the mass per unit volume with SI units of kilograms per meter cubed. The reciprocal of the mass density is the specific volume given the symbol V hat. The specific volume is the volume per unit mass with SI units of meters cubed per kilogram. What is the relationship between molar density and molar concentration?
Density and concentration. So we can say that we have 1 mole of oxygen is equal to 1 mole of nitrogen in some ways, and that like the chemical interaction is good. And molarity, I remember, isn't it over the volume? But I'm not sure about the density and concentration.
This is like my A-level chemistry knowledge. I've forgotten already. Wait, moles is no more Mr. Nice Guy. Number of moles is equal to the... what's the relationship between molar density and molar concentration? Oh wait, molar density. Okay, that's a new term. I've only heard of molar concentration.
Molar density and molar concentration. I would think that molar density is how many moles are in a mass, and molar concentration is like a percentage rather than a number.
Not sure about that one. It's one of them is the concentration, one of them is the density.
Molar density is probably going to be the amount of atoms, or atoms in a specific volume. And then molar concentration is going to be, I think, like the ratio of a set of atoms, like a particular set of atoms to another different elements, if you're looking at like molar concentration in some material, I think. I don't know.
How would you use molar density?
Going back to the example that I was thinking, like you can have nitrogen, one molar of nitrogen, or 1 molar of nitrogen, but that corresponds to different mass and probably different volumes. So I think it might be easier in some cases that you want to work off volume, you can just use straightforward density, or in other case, if you just have like a volume and you just want mole, you can just go by that as well.
I mean, finding some partial fraction information, I guess.
I think I'd use it to find the way that mass and volume are related for a particular element, with like if you know the element and like the element that makes it up, I think.
Probably calculating the amount of moles in an object.
I guess molar density is probably like something to do with like moles per unit volume. So I would probably use it to like calculate how many moles of a particular compound there is within a certain volume.
The molar density, also given the symbol ρ, is a measure of the number of moles per unit volume, with SI units of gram moles per meter cubed, but chemists lean toward moles per liter. The reciprocal is the molar volume or specific molar volume, also given the symbol of V hat, with SI units of meters cubed per gram mole. We reuse the symbols for mass density and specific volume for molar density and molar volume. You have to check the units to see which is which. Closely related to density or mass density is the specific gravity. The specific gravity is the ratio of the density to a reference density. The most common reference density is liquid water at 4 degrees Celsius. This is a density that you should probably memorize. The density of water at 4 degrees Celsius is 1,000 kilograms per meter cubed, 1.000 grams per centimeter cubed, and 62.43 pounds mass per foot cubed. The molar concentration, or simply concentration, is the number of moles per unit volume, so it has the same units as molar density. It is usually given the symbol C. For species A, C sub A equals N sub A over V. For an ideal gas, it can be calculated as C sub A, or N sub A over V, is equal to P sub A, or the partial pressure of A, divided by RT, the gas constant times the absolute temperature. The mass concentration, also usually given the symbol ρ, is the mass per unit volume. It has the same units as density. It is most often used for quantities such as salinity, which is the mass of salt in a volume of seawater. Rho sub A equals the mass of A over V. You have to determine the context to determine if you have a mass density or a mass concentration. The mass flow rate, m dot, is simply the amount of mass flowing past a given location in a period of time, with SI units of kilograms per second. For open, steady-state systems, the sum of the mass flow rates in equals the sum of the mass flow rates out. In equation form, the sum of the mass flow rates of species I in equals the sum of the mass flow rates of species I out. Again, this is specifically for an open, steady-state system. The molar flow rate, n dot, is the number of moles flowing past a given location in a period of time, with SI units of gram moles per second, but it's often expressed in kilomoles per second. For open, steady-state systems with no reactions, and the no reaction part is important, the sum of the molar flow rates in equals the sum of the molar flow rates out. For reacting systems, it is generally not true that the moles in equals the moles out. Several later videos will deal with the molar flow rates in reacting systems. For open, steady-state systems with no reactions, the equation form is the sum of the molar flow rates of species I in has to equal the sum of the molar flow rates of species I out. The volumetric flow rate, V dot, is the volume of fluid flowing past a given location in a period of time, with SI units of meters cubed per second. In general, for open steady-state systems, the sum of the volumetric flow rates in is not equal to the sum of the volumetric flow rates out, because specific volume can change with temperature, pressure, and composition. For a specific location in space and instant in time, the following relationship exists among the volumetric flow rate of a fluid, the average fluid velocity, and the cross-sectional area of the fluid. The volumetric flow rate, V dot, is equal to the fluid velocity, U, times the cross-sectional area, A, which is the area normal to the flow direction. For an open, steady-state system, the expression is true at any location in the system. The relationship between mass flow rate and volumetric flow rate is that the mass flow rate, m dot, is the fluid mass density, rho, times the volumetric flow rate, v dot. For an open, steady-state system with one inlet and one outlet, the mass flow rate in equals the mass flow rate out, which means that the fluid density in times the volumetric flow rate in equals the fluid density out times the volumetric flow rate out. Both the fluid density and the volumetric flow rate can change, but their product must be constant. Don't forget, volume is not a conserved quantity. Just because the mass or molar flow rate is constant, it does not follow that the volumetric flow rate is constant. How is the velocity of a fluid in a pipe or a tube defined?
I think you can go about it two ways. You can explain it as like how much mass is going through per time, like 1 kilometer. Not kilometer, that's a unit of length, but it's like 1 kilogram coming out of a tube per an hour versus like you can go about it the other way, just like volume, like 1 liter coming out of the tube per hour.
Oh, probably like, so like how fast a liquid travels in a pipe, so like the meters per second.
So you'd use Bernoulli's, and then I know like the velocity of outflowing fluid is like the square root of like 2gh, but like in the fluid, it's just like it's what flow rate over time.
But I think it would be like the average velocity of a certain set of molecules flowing through that tube.
It depends, like the average of the flow rate over the area usually.
How do you define the velocity of a fluid? Recall that the volumetric flow rate is equal to the fluid velocity times the cross-sectional area, meaning that the fluid velocity is the volumetric flow rate divided by the cross-sectional area. And if you have a stopwatch, a measuring cup, a pair of calipers, and fluid flowing in a tube at a constant rate, how would you measure the fluid velocity?
I mean, since it's constant, I don't really think much about using all the tools. So if you have like a measuring cup that has like a unit on it already, you can just do it as brief as you want, because like one of the constraints, let's say, is constant. If I just do it for 1 second, I just get the same rate as I calculated for an hour.
Oh, fluid rate? Okay, well, I guess I'd use the caliper to measure the diameter of the tube. Then that would give me like, I could use that diameter to calculate the cross-sectional area of the tube. I think the cross-sectional area is the more important one. And the measuring cup, I guess water or like the liquid or the fluid would flow through the cup, land in a tube, and have like 0 volume. And then, I don't know, I'd measure for like a period of like 10 seconds or however many seconds, let the liquid flow. And then when 10 seconds has reached, I would like stop the stopwatch. And I probably, wait, I don't know, I don't know how much water has come out, do I? I'm actually not too sure then. Yeah, then in that case, I'm not too sure.
Okay.
I guess I would determine like a period I want to measure the water flowing outwards out from the tube into the cup, and then after, like, I'd count to like, say, like, I don't know, 5 seconds, and then after that I would stop the water from going into the cup, measure the amount of water with the calipers. That would be, so I would measure, and then I would determine what the area or the volume of the cup. So I determine the volume of the cup, the amount of water that flowed into the cup, and with the time, I'd be able to find the velocity using some equations.
So you can time the amount of time it takes for a set volume to drain, and then you can find at least like the average velocity of that volume as a function of time.
Yeah, probably the easiest way would just be to do total volume that gets distributed. So I know that I can measure the diameter of the pipe or the tube, right? Use that to fill up my container with a given time, and find the volumetric flow rate by backing that out, and then from there just divide by the area to get the velocity of the flow.
If you have a measuring cup of volume V and a stopwatch, you can measure the time it takes to fill the measuring cup and calculate the average flow rate as V over T. For a tube, the cross-sectional area is pi times the inside diameter squared over 4, and the fluid velocity is the cup volume divided by the fill time and the cross-sectional area. For reference, in laminar flow in a tube, the average velocity is half the peak velocity, and the velocity varies from 0 at the boundary walls to twice the average velocity in the center. The takeaways from this video are: 1. Mass density or density and specific volume are reciprocals. 2. Molar density and molar volume are reciprocals. 3. The mass flow rate is equal to the density times the volumetric flow rate. 4. Fluid velocity is defined as the volumetric flow rate divided by the cross-sectional area. 'Thanks for watching. This video was brought to you by the DOFPro team.